Hello everyone, I'm Nengwen from Tsinghua University. I'm going to talk about real-time incident prediction for online service systems. This is a joint work with collaborators from Tsinghua University, Tianjin University, China EverBright Bank, BizSeer, and Beijing University of Post and Telecommunications. My presentation includes 4 parts: background, approach, evaluation, and discussion. First, let's start with the background of this work. Nowadays, online service systems such as search engines, online shopping, and social network have become indispensable parts in our daily life. Ensuring service reliability and user experience are vital for these software systems. Although tremendous efforts have been devoted to software service maintenance, incidents are still inevitable due to their large scale and complexity, which could lead to system unavailability, poor user experience, and huge economic loss. To reduce the influence of incidents and guarantee the quality of software services, there are 2 widely used ways in both academic and industry. One is to mitigate the already happened incident as soon as possible, and the other is to predict the occurrence of an incident in advance, so that engineers can take some proactive actions to avoid it. Our work focuses on the second way, since this way is able to directly avoid the occurrence of service incidents rather than reduce the time of service unavailability. In the literature, many efforts have been devoted to incident prediction, such as predicting disk failures, load failures, switch failures, and equipment failures, but they still suffer from various limitations in practice. First, the majority of existing works target at the prediction of a specific type of failures. Moreover, these prediction approaches utilize logs or metrics to extract omen patterns for predicting the specific type of failures. However, tens of TBs logs and more than thousands of metrics tend to be generated per day for a large-scale system, which could bring great challenges and costs to learn a prediction model from massive data. Due to the difficulty of handling log data and metrics, in this work, we normally focus on incident prediction with alerts. For online service systems, alerts are a key data source for recording the anomalies generated from various system components. More specifically, monitoring systems continuously collect various data, for example metrics, logs, and traces, and engineers manually define many rules to check this monitoring data to ensure service quality. When a certain rule is violated, an alert would be generated to report the anomaly. This table shows examples of alerts with many attributes. Air Alert was proposed recently to predict general incidents and relies on lightweight alert data, but its performance is unsatisfactory since it just concedes the number of different types of alerts for prediction. By communicating with our industry partners, they confirmed the importance and feasibility of incident prediction based on alerts, and they have 2 popular practical methods. The first one is to manually summarize a set of prediction rules based on their experience and domain knowledge. For example, if the alert with the keyword TCP is not responding appear at least once, last for at least 3 minutes, involve 4 different servers, and do not happen in the period of software change, engineers infer that the involved servers would be down. However, the rule-based incident prediction method performs not well, because it is time-consuming and tedious to manually summarize these rules from a large amount of historical data. Besides, the design and maintenance of the rules require experienced experts with rich domain knowledge. Also, the rule-based method cannot adapt to the dynamic environment, causing that engineers have to spend many efforts in manually checking and re-summarizing the rules. Another way is to use the technique of association rule mining to automatically discover omen alerts for incidents. For example, if an alert always happens before an incident, this alert would be used to predict the incident. However, according to the feedback from engineers, this method can only cover a very small set of situations since most incidents do not have frequently associated alerts and cannot be accurately predicted in this way. In this work, we formulate the problem of incident prediction as time window classification. As shown in this figure, for the current time, we get the observation window. Then we use alert data within the observation window to predict whether an incident will occur within the prediction window. Lead time is the minimal time interval that engineers need to react to an early warning. However, predicting incidents based on alert data in practice also faces several challenges. First, alert data contain tens of attributes, and thus how to extract useful information from alert data is challenging. Second, not all alerts before the occurrence of an incident are helpful for prediction, and the noisy alerts would destroy the prediction performance. Thus, how to reduce the influence of noisy alerts is the second challenge. The third challenge is, in addition to accurately predicting incidents, an interpretable result should be provided to engineers in order to facilitate them to understand and handle this incident. Then I will talk about our approach in detail. To tackle the above challenges, in this work, we propose a real-time and lightweight approach named eWarn, aiming to give an early warning signal of incoming incidents. This figure shows the overview of our approach, including 4 main steps. First, eWarn conducts feature engineering to identify a set of effective and interpretable features from alert data in an observation window to overcome the first challenge. Second, eWarn incorporates multi-instance learning to distinguish helpful alerts and noisy alerts in an observation window to overcome the second challenge. Third, based on the set of training data with identified features and labels, eWarn further deals with class imbalance problem and builds a classification model via machine learning, which is used to predict whether an incident will occur within a prediction window based on incoming alert data in real time. Fourth, after predicting an incident, eWarn sends an early warning to notify on-call engineers. In the meanwhile, eWarn adopts LIME, a state-of-the-art explanation technique, to interpret the prediction results for engineers to facilitate the understanding and handling of the incident, which is used to overcome the third challenge. About the feature engineering component, we identify 2 types of features from alert data, textual features and statistical features. About textual features, we adopt the technique of topic model to extract the textual representation vector of alert content, denoting the hidden semantic information. As we mentioned earlier, a big challenge in our problem is how to reduce the influence of noisy alerts, because not all alerts in an observation window are helpful, and the omen alerts may be flooded in the non-omen alerts. To tackle this challenge, we propose to adopt the idea of multi-instance learning. For incident prediction, it is also more reasonable to assume that at least one instance before the occurrence of an incident carries an omen signature than to assume that all the instances in the observation window carry an omen signature. In our approach, eWarn identifies omen alerts and noisy alerts by the method of clustering because we observe that omen instances tend to be similar and appear more than once in training data, while non-omen instances tend to be various and even chaotic. Therefore, we use the clustering-based feature aggregation to assign larger weight for omen alerts and smaller weight for noisy alerts. After feature engineering, eWarn will build a classification model based on XGBoost model and adopt oversampling with SMOT to avoid class imbalance. More importantly, eWarn also provides an explanation report about the prediction along with the early warning to facilitate engineers to understand and handle this incident in practice. We adopt LIME to explain a prediction result by providing relative feature contributions for a single sample to the prediction result. This figure presents an example report for engineers. Well, let's move on the evaluation part. In this study, we used 11 representative online service systems from a large commercial bank, which supports more than 100 million users and includes hundreds of service systems. To show the effectiveness of eWarn in incident prediction based on alert data, we compared eWarn with 3 baseline methods. Air alert is the state-of-the-art alert-based incident prediction approach and uses the number of different kinds of alerts as features and utilizes XG booths to conduct binary classification. TF-IDF LSTM is proposed to predict cluster failures based on log data which can be adapted to our problem. It uses TF-IDF to extract textual features from the observation window and uses LSTM to predict incidents. FP growth is a classical association rule mining method and can be used to predict incidents by mining the correlated alerts that always occur before incidents. This table shows the precision recall and F1 score comparison results between our approach and this compared method for 11 online service systems. From this table, we can observe that our approach outperforms all the 3 compared approaches on average in terms of all the measurements. About the contributions of 3 main components in eWarn to its overall performance, including the multi-instance learning formulation, the feature engineering component, and the classification model building component. We also prove that each component is an indispensable part in our approach by solid experiments. Then I will discuss some observations and lessons learned in our study. We want to discuss the relationship between incident prediction and incident diagnosis. Although eWarn is designed for incident prediction, it can also assist engineers for incident diagnosis. Even though interpretable results provided by eWarn may not directly pinpoint the root cause of an incident, for example, hardware errors, misconfigurations, or software bugs, they can provide useful clues to narrow down the search space of diagnosis. When eWarn gives a positive result, the interpretable analysis component will tell engineers which feature makes the largest contribution to the predicted result. The most important feature may be closely related to the root cause of the incident. We also obtained some lessons learned in our study. First of all, in spite of the effectiveness of eWarn in predicting incidents, we have to admit that not all incidents can be predicted well in advance. More specifically, some sudden incidents caused by unexpected factors, for example power outage, are difficult to be predicted. In our study, we find that application-level incidents are more easier to be predicted. This is because high-level incidents are generally caused by faults in the low-level components, for example server, database, and network. Second, prediction window size is important for incident prediction. Also, incremental updating is necessary to adapt to frequent software changes. About more details of our work, like detailed approach, parameter analysis, and more discussions you can find in our paper. Finally, let me conclude my presentation. Incident prediction could give an early warning signal and make engineers take proactive actions to prevent the incoming incidents and ensure the quality of software services. We propose eWarn, a novel approach to predicting general incidents based on alert data. 3 key ideas of our approach are an effective feature engineering component to deal with complex alert data, multi-instance learning to handle noisy alerts, and interpretable analysis to facilitate the understanding and handling of incidents. An extensive study on 11 online service systems in a large commercial bank and deployments in the real world show the effectiveness and practical performance of our approach. That's all. Thank you for your attention.